In this particular lecture, I want to talk about something called a tangent line. But before we can talk about a tangent line, we have to start off by talking about something called a secant line. All right, so what is a secant line? Well, when we're talking about tangent lines, secant lines, we're talking about them in relation to some graph or some curve. Right, so let's say we had a curve out there in two-dimensional space, and we wanted to find a secant line. Again, what does that mean? Well, a secant line is found by coming in and picking 2 points on the graph. So I'm going to pick 2 points here basically at random. And what I would then do after choosing those points is I would find the straight line that connects those 2 points. That is a secant line. Secant line, again, is formed by picking 2 points on a graph and finding the equation of the line that connects those 2 points. So, just in case it's been a while for you, here are some things that we're going to put to use that you are supposed to already know. First of all, the slope of a line, as it's defined up to this point in time for you, is y2 minus y1 over x2 minus x1, which can also be written as f of x2 minus f of x1 over x2 minus x1, if you want to write it using function notation. So that's something you're supposed to remember. You're also supposed to remember that the equation of a line is most often written as y equals mx plus b, but can also be written as y minus y1 equal to m times x minus x1. Again, these are things you're supposed to already know because they would be used in the finding of this secant line as you see there in the drawing. Okay, so let's actually put that to use. Let's find a secant line. Let's actually do it. Let's look at the curve y equals x squared, simply because the calculations will be easy. I won't lie, I'm not looking for difficult arithmetic right now. So y equals x squared, it's a parabola that sits on the origin. And let's say that I was wanting to find a secant line between the points 1, 1, and again, how did I get that? Well, the x value of 1 I just sort of randomly chose, and I plugged the 1 in for x here, and I got the y here. And let's say we're also interested in the point that has the x value of 2, and plugging a 2 in here gives me the ordered pair 2, 4. So if I wanted that secant line, the way I would find it is to first of all find the slope, which is y2 minus y1 over x2 minus x1, and it's a 3. So my slope is 3. All right, using the y equals mx plus b, and also using the ordered pair 1, 1, I'm going to find my y-intercept. So the y value of 1 is equal to the m value of 3 times the x value of 1 plus the b. Subtracting, this gives me a b of negative 2. So therefore, the secant line between these 2 points is y equal 3x minus 2. Okay, that's the secant line. Now the vocabulary secant, that terminology, may be new to you. Not to be confused with the secant trig function. All right, not to be confused with that. But that use of the terminology may be new to you, but none of this should be. You should be very familiar with taking 2 ordered pairs and finding the line in between them. All right? But again, the title of today's lecture was not secant, but tangent line. All right? So what is a tangent line? If we come back to this first drawing, the tangent line is found by finding the line that touches the curve not in two places, but in only one. All right? And so therefore, for this point, the tangent line would not look like this because it's hitting it twice, but the tangent line would look a bit more like that. Now, granted, I said hits the curve in only one point, and you will notice that if I extend it far enough, it's eventually going to hit again. Okay? Well, this we're not worried about. This we're not going to do. All right? Basically, with a tangent line, what you're looking for is the line that hits the curve only once in some close proximity to the point. You're not so worried what's going to happen a mile away. You just want it to hit the curve in one point and only one point when you're close to that point. And the reason for this, the one thing that you've studied quite a bit, maybe studied the most in an algebra setting, is slope. And what we're getting into right now this semester has everything to do with slope. But the problem is this definition has one big weakness. The definition you've always used for slope has a problem. And the problem is, no matter which version you use, you got to have two ordered pairs. Okay? You have to have two ordered pairs. And as you can see here, when I talk about the tangent line, I want the line that hits the curve in one place and one place only. Therefore, I cannot use the old definition of slope. I've got to find a new way to find slope because I don't need to find the slope between these 2 points. I need to find the slope at this one and only one point right here. Because this slope constitutes an average slope. All right? This one that we calculated just a minute ago with the parabola is an average. All right? If I was to move this point and draw a new line, and it's hard to see with this drawing, but that slope would change. New point and new line, the slope changes. All right? We can demonstrate that. If we want to use an x value of 1.5, if we want to get a little bit closer, then what we can do is find the slope not between x values 1 and 2, but between x values 1 and 1.5. All right, so again, since I'm still stuck with this weak definition of slope, I'm going to have a couple of ordered pairs again. This time my ordered pairs will be 1, 1. That's what I had before. But the other one is going to have a y value that corresponds to a 2.25, because that's what you get when you square. That's what you get when you plug it in. All right, so this time my slope's going to be 2.25 minus 1 over 1.5 minus 1. And this is a 1.25 over a 0.5. It comes out to be 2.5. Okay, so since I moved closer, you should be able to visually be aware that this line is going to start going a little bit more downhill. And that's why the slope went from a 3 down to a 2.5. I would then repeat the rest of the process. I would say my y value at the point in question, which was 1, is equal to the slope, which was a 2.5, times the x value, which is a 1, plus the b that I'm looking for. And when you take 1 and you subtract off the 2.5, you get a b value of negative 1.5. So this new line is y equal to 2.5x minus 1.5 compared to the old. You see the slope is smaller because you came back closer to the 1, and the y-intercept is a little bit higher up because you've angled it in that direction. All right. So again, my problem is I'm stuck with this old school definition of slope where you have to have 2 points. And frankly, for today, or at least for this material right now, we're going to remain stuck, okay? And so how would I get a better and better and better and better estimate of the slope at 1? Well, I will do it by using ordered pairs that get closer and closer and closer. All right, so if I was to redraw this parabola, hopefully maybe this time do a slightly better job of it. If this is the point 1, 1, and you want to know, if you want to figure out what is the slope of the tangent line, the way you will do it is by repeatedly finding the slope of secant lines. So again, we started out here at an x value of 2, and we found that secant line. We then moved to 1.5, and we found that secant line. Where would you go next? You'd go 1.4, 1.3, 1.2, 1.1, 1.01, 1.001, etc. And you could, if you wanted to, if you were that curious, you could come from the other side. You could use a 0.9 and find the slope of that line, 0.99, 0.999, and you would find that one slope in particular was starting to show itself. By coming closer and closer and closer and closer to 1 from both sides, you would start to see the true slope at 1. This can be done as I've done here when you have the function and you can pick your x's and plug them in. You can do it that way. It can also be done, and has been done, by data tables, just charts full of information. Let me do a quick screen share with you and pull up a page here. And as you can see with some of these problems, what you're being given, we'll get a little bit further along, is a table of values, all right? And if it said, for example, what the point we're curious about is this 15,250, which is right here, and using different t values, t value of 5, and then 10, and then the 20, and then the 25, then the 30, use these ordered pairs, make sure you arrange them so you're coming at this point from both sides, and see what kind of slope you're getting closer and closer to. You can do that through an averaging process. Right? You can average your answers and see what kind of slope you're getting to. Also pay attention to what's coming as you come in from both sides, as I did on that piece of paper. All right? So pay attention to that as well. All right? So you may be wondering, how is this relevant to anything? How is this relevant to anything at all? Well, what this leads us to, the first question that we can start to answer with this is an answer to a question concerning velocity. Right? Velocity. All right? What's the deal with velocity? Well, on your car, you have something called a speedometer, and that was horribly written. Let me have another try. Maybe that's a little bit better. On your car, you have something called a speedometer. It tells you how fast you're moving at any point in time. Okay? So they want to talk about velocity. Let's just sort of simplify a little bit. Let's talk about speed. Okay? What is speed? What is speed? Well, speed is the change in distance over the change in time. In other words, it's how far you travel over a certain period of time. Now, there's a better way to write this. In math classes and calculus in particular, we'll use the Greek letter delta to mean change in. So I could rewrite this as delta D over delta T. And that's one way to express speed. All right? So if I were to draw for you the graph of the movements of a car, all right, let's say that that on the x-axis, we're going to tell you what time it is, and on the y-axis, we're going to tell you what distance has been traveled at that time. All right, and if I'm going to try and make this look familiar, if that curve looks something like this, it might remind you of that parabola curve. And I started to draw a part over here, but we don't need that part. We need just this part. All right. So if I was saying, okay, what approximately is your speed at time 10 minutes? Well, you could come up here and you could find a point on that curve, but all that point would tell you is what distance you've traveled in 10 minutes. So how would I figure out how fast I was traveling at this time if all I know is distances at a particular time? Well, what I could do is say, well, for speed, I need to know change in distance over change in time. So that implies, this whole change in implies I need 2 points. So what I could do is say, well, I'm going to pick a point right here. Let's say I'm going to pick a point that corresponds to 12 minutes. And let's say in 10 minutes, I've traveled, I don't know, 3 miles. And in 12 minutes, I'm now up to 5 miles. Well, if you come in here and sort of superimpose a little triangle, you see that my change in time is on the horizontal, and that's a 2-minute change in time. And my change in distance is on the vertical, and that's also a change of 2. Therefore, my delta D is 2, my delta T is 2, my speed is what? Well, if time is in minutes and distance is in miles, that is 1 mile per minute, which, by the way, if you do some unit conversion, it's 60 miles per hour. I'm doing 60 miles per hour if I have traveled 2 miles in 2 minutes. So how was my speed found? My speed was a slope. You should recognize all of this as being slope. I just took the ordered pairs 10, 3, and 12, 5. And I took those 2 ordered pairs and I turned them into a speed ultimately of 60 miles per hour is where that ended up. Those 2 ordered pairs turned into a 60 mile per hour movement of that automobile. So our slope question, our secant question, which turns into a tangent question, is going to turn into quite a few different applications, one of them being speed, which we will then turn to velocity. Velocity is nothing but the vector version of speed, because what slope is, what you should have heard in the past, is that slope is nothing more than rate of change. All right, so when things are changing, slope is measuring how they change. When you're finding slope between 2 points, what we just found right here with the 60 miles per hour, don't be misled. What we just found is that this car is traveling 60 miles per hour on the average. This is an average speed. If you were to use two different points, you'd come up with a different number, all right? And since this curve is just that, it's curved, what we find is that the speed is changing at all times, okay? This car is not sitting on 60 miles per hour, all right? If it were, then what we would have is a straight line. The curve that described the movement of that car would be a straight line if they were sitting flat on 60 and never changing. This car is changing its speed at every instant in time. All right. So the secant, again, using two ordered pairs, has given us an average speed. What we want to work towards is finding instantaneous speeds. So what we want to work towards is secant lines becoming tangent lines, because the tangent line is the instantaneous, whereas the secant line is nothing more than an average.